Okay, now we're going to look at phase 2 of glycolysis. And this is the energy recovery, or the payoff, if you wish. This involves reactions 6 to 10. And during this phase, 2, keep in mind, molecules of GAP, or glyceraldehyde 3-phosphate, are converted to 2 molecules of pyruvate. During this process, we generate 4 ATP, which allows us to pay off the energy debt that we incurred in phase 1 and net 2 ATP. Okay. So we're going to pay off phase 1 debt, and we're going to net 2 ATP. Okay. So, starting with reaction 6, which is, of course, we're going to start with glyceraldehyde 3-phosphate. And in a reversible reaction, generate 1,3-bis phosphoglycerate. Okay. And, oops. Hold on a second. Sorry about that. So some things we're going to need here. We're going to need NAD+, and a molecule of inorganic phosphate. So we are going to reduce NAD+ to NADH. We'll also generate a hydrogen ion, and that inorganic phosphate then is going to be added to glyceraldehyde 3-phosphate, and the enzyme that is required here is glyceraldehyde 3-phosphate dehydrogenase. Or GAP DH. Okay. So in this reaction, we've got a reduction and a phosphorylation. Of course, there also has to be an oxidation too, and that is the oxidation of glyceraldehyde 3-phosphate. So, starting with, and also by the generation of that NADP, this step also generates the first high energy intermediate. Because the energy that is extracted from these molecules comes from high energy bonds. Okay. So, beginning with glyceraldehyde 3-phosphate, or GAP. And we have that NAD+. and inorganic phosphate. Reduction of NAD plus to NADH. And then we have GAP DH, which is dehydrogenase, basically transfers electrons. It's also an oxoreductase. Electron transfer. And of course, then our product there we go. Okay, to move that up. 1,3-bisphosphoglycerate. Okay. Oh, I didn't give you the notation up here. 1,3-BPG. Okay. So in reaction 7, we're going to generate our first 2 molecules of ATP. Keeping in mind, we have, even though we're only showing one of these intermediates, there are 2 1,3-bisphosphoglycerates resulting from the 2-glyceraldehyde 3-phosphates. So 1,3-bisphosphoglycerate to 3-phosphoglycerate. One 3 BPG to 3 PG. The enzyme involved here is phosphoglycerate kinase. Whoops, there's that word kinase again. It is dependent on magnesium ion. And this reaction is a substrate level phosphorylation. We also, as I said, generate ATP. Whoops, it should be ADP, sorry about that. ADP in, ATP out. Okay. So what is a substrate level phosphorylation? It is the phosphorylation of where actually it generates ATP by taking a phosphoryl group from a metabolite or intermediate molecule, in this case glycolysis, and transferring that phosphoryl group to an ADP molecule to produce ATP. And this step pays off the ATP debt from phase 1. Okay. So as we look at the reaction, actually I meant to write that in red, but that's okay. Phosphoglycerate kinase, ADP, ATP. This also is a regulated step. And we get 3-phosphoglycerate kinase. Oops. Sorry, move that up a little bit there for you. 3 more reactions. And we need to make 2 more molecules of ATP in order to gain from this pathway. Oops. So reaction 8. We have our 3-phosphoglycerate. And this gets converted to 2-phosphoglycerate. So essentially this is a rearrangement. And we'll just be moving that phosphate group from carbon 3 to carbon 2. And the enzyme involved here is phosphoglycerate mutase. And as I said, it's a rearrangement. But mutases, or amutase, catalyzes the migration of a functional group within a substrate. And so we are just going to move that phosphate again to carbon 2. This is PGM. This also introduced, jumping ahead of myself, never mind. That will be in the next step. All right, so 3PG to 2PG. Now the next reaction is the formation of a second high energy intermediate. So reaction 9. Two phosphoglycerate to phosphoenolpyruvate. Getting close. See that word pyruvate. PEP. High energy. Okay? So 2PG is converted to PEP, and the enzyme here is enolase. Basically, this is a dehydration of 2PG to form a double bond, which will release more energy when it is hydrolyzed. So we're introducing a double bond into this molecule. And as I said, this is formation of a second high energy intermediate. So again, starting with 2-phosphoglycerate, enolase, no notation for this one. And, oh, I didn't add this up here. We also get a molecule of water. Remember I said this is a dehydration that introduces that double bond. And the last reaction, we produce 2 ATP because we have, remember, 2 PEPs that are going to be fed into reaction 10. So phosphoenolpyruvate this reaction goes in one direction only. And we'll see how we get around that in gluconeogenesis. It's going to require a 2-step process. Whoops. Pyruvate kinase is our enzyme. It requires magnesium and potassium ions. And this is the second substrate level phosphorylation. And it generates 2 net ATP. So this is where we gain or net those 2 AP overall, but that also means that we have ADP getting converted to ATP, and we also need some hydrogen ion. So we have our PEP. and finally pyruvate. So PEP, pyruvate. Now pyruvate has several fates, or 3 fates, and we'll be discussing those, or I think I've already discussed them maybe in the following video. So we will talk about it again. But before we end, I just want to discuss the overall reaction of glycolysis and make a few comments about the products. So the overall reaction is glucose plus 2 NAD plus 2 ADP plus 2 inorganic phosphates that will give us 2 pyruvate, 2 NADH plus 2 ATP plus 2 waters and 4 hydrogen ions. Okay. So the 3 energy-related products of glycolysis are 1, ATP, obviously, and of course in phase 1 there is an initial investment of 2 ATP per glucose, and then the subsequent generation of 4 ATP in phase 2 by substrate phosphorylation. So we pay back our initial investment and net 2 ATP. The second high energy molecule or energy related molecule that's produced is NADH. Glucose is oxidized and NAD plus is reduced. Remember, oxidation and reduction are coupled processes, and it's reduced to, of course, NADH. NADH itself is a source of free energy. That can be recovered by its oxidation. In other pathways, and we will see that oxidation occurring, particularly in the electron transport chain. So the NADH and pyruvate can be utilized differently depending upon whether conditions are aerobic or anaerobic. So under aerobic, AERO, there we go. The electrons are passed from the reduced molecule to electron carriers. And finally, to O2. O2 being the acting as an oxidizing agent in the electron transport chain. And I'm just going to call that ETC, electron transport chain. We'll be talking about that after we discuss the citric acid cycle. And this then drives ATP synthesis. And this is where our largest pool of ATP comes from. NAD can also be regenerated, so it can participate in further rounds of catalysis that are mediated by glyceraldehyde 3-phosphate dehydrogenase, and we'll see that as well. Lastly, let's look at pyruvate. And again, we get 2 pyruvate per 1 glucose molecule that is oxidized, or partial oxidation of glucose. These are still relatively unreduced molecules. Which means we can get some energy out of them. And if we have aerobic conditions, pyruvate will be oxidized to CO2. So completely. And that occurs in the citric acid cycle, or the TCA, which we'll be talking about next. The energy released in this process is going to drive the synthesis of much more ATP than is generated by the limited oxidation of glucose in glycolysis. And if we have anaerobic conditions, pyruvate is oxidized to a lesser extent to generate NAD+. And this is actually the process of fermentation. Okay, that concludes the discussion of the actual reactions in glycolysis, phase 1 and phase 2. So enjoy your next video.